friends. In this session, let's have a quick recap on the topic enzyme inhibition. Different types of enzyme inhibitions include commutative inhibition, non-commutative inhibition, uncommutative inhibition, suicide or feedback inhibition. Now, let's compare between commutative, non-commutative and uncommutative inhibition first. In commutative inhibition, the inhibitor is a structural analog of the substrate and therefore it competes with the substrate to bind to the active site of the enzyme. Here, the inhibitor binds to free enzyme only and it competes with substrate for binding to the free enzyme. Therefore, increasing the concentration of the substrate overcomes the inhibition. In non-commutative inhibition, the inhibitor binds to a site other than the active site of the enzyme, say allosteric site, and it inhibits the enzyme. But here, the inhibitor binds to both the free enzyme as well as the enzyme substrate complex. Therefore, increasing the substrate concentration cannot overcome non-commutative enzyme inhibition. In uncommutative inhibition, the inhibitor does not have any affinity for the enzyme and therefore it cannot bind to the free enzyme. Here, the inhibitor binds to enzyme substrate complex only and not to the free enzyme. Therefore, increasing the substrate concentration favors inhibition by the inhibitor. Now, let's go through the graphs that depicts different types of inhibition. We can focus on the double reciprocal plot, which plots 1 by V on the y-axis and 1 by S on the x-axis. We get a straight line and intercept on x-axis is negative 1 by Km. We draw the graph in the presence and absence of inhibitor. First one, commutative inhibition. In the presence of commutative inhibitor, Vmax is unchanged, but Km value is increased. Since Km value is increased, 1 by Km decreases on the negative x-axis. The two graphs, both in the presence and the absence of inhibitor, intersects at the y-axis. Second one, non-commutative inhibition. In the presence of non-commutative inhibitor, Vmax is decreased, but Km value is unchanged. The graph shifts upwards since 1 by Vmax increases. The two graphs intersect at the x-axis. Third one, uncommutative inhibition. Here, both Vmax and Km decreases in the presence of inhibitor. Therefore, 1 by Vmax increases and 1 by Km also increases in the negative x-axis. Therefore, we get two parallel lines on double reciprocal plot. Let's look at the few clinical applications related to commutative enzyme inhibition. First one, antibacterial drug sulfonamide. Sulfonamide being structural analog of PABA, that is para-aminobenzoic acid, it commutatively inhibits folic acid synthase enzyme that is necessary for folic acid synthesis in bacteria. Second example, anti-cancer drug methotrexate. Methotrexate being a folic acid analog, it commutatively inhibits dihydrofolate reductase enzyme that is necessary for DNA synthesis and cell division. Third example, anticoagulant drug dicumarol. Dicumarol being a structural analog of vitamin K, it commutatively inhibits vitamin K activity. Last one to be discussed is suicide inhibition. It is a system by which the cell regulates the production of some products based on the concentration of the products. Here, the inhibitor is converted to a more potent inhibitor by the enzyme to be inhibited. It is a reversible inhibition since this potent inhibitor binds to the enzyme covalently. Let's look at an example. The mechanism of action of allopurinol, an anti-gout drug, is based on suicide inhibition. The final product of degradation of purine, as we know, is uric acid. In this reaction, hypoxanthine is converted to xanthine as xanthine is further converted to uric acid by the enzyme xanthine oxidase. The anti-gout drug allopurinol is oxidized by xanthine oxidase to alloxanthine, which is more potent inhibitor of xanthine oxidase. Thereby, it decreases uric acid production.